Okay. Hello, dear Meatbags. Now is the second lesson on mini course for hyperbolic geometry. And today we will not talk much about hyperbolic geometry, but we'll talk mostly about multidimensional geometry. So let me open the slides I prepared to you. Okay, so previous time we stopped by the notion that we are motivated for example, somehow visualizing hyperbolic space and working with four-dimensional space, I mean Euclidean four-dimensional space. So today we are going to learn how to think in this four-dimensional geometry, how to think in multidimensional geometry, how to live in it, how to act in it, probably. But firstly, how to define this. So, what is an abstract definition of this? So, if we have n numbers, we can consider them as coordinates like we do in two-dimensional geometry or three-dimensional geometry. There are the same number of coordinates, and this and the set of all such n-tuples form many n-dimensional space. Well, that's some form of definition. We can define some things about it, prove some theorems about it, and of course we can work in this setting from abstract point of view, but sometimes we are motivated to have some intuition in it, and for example, to find some interesting phenomena. Why? Because, yes. Okay. Yeah, so what for? Actually, usually our data is presented as many numbers, some sequence of numbers, maybe not very related to each other. For example, like data of of people's weight, age. I don't know how to say this. Geographic coordinates of their birth. I don't know. Whatever numbers do you like to present in your data. So actually, we are if we are data scientists, if we are data analysts, we just working usually in many dimensions. Well, so we usually not working with them only with machines. Sometimes we need to work with them visually. And how to visualize them, actually. Yeah, that might be some problem. Okay. So, I prepared for you several videos and several speeches about how do you, how do you imagine multidimensional geometry. So the first series of videos is Dimensions movie. It will start very slowly, but it will gradually explain some important concepts from 4 dimensions. Okay.
My name is Hyperbolic. I lived in the 2nd century before the birth of Christ, and I don't think I'd be right if I told you that I am the father of the sciences of geography and astronomy. You know, I wrote more than 14 books, but unfortunately they have almost all been lost in the mists of time. I was responsible for the first catalog of the stars, founded the field of mathematics called trigonometry, and even invented the astrolabe. Fortunately, my brilliant successor, Ptolemy, 3 centuries after my time, inspired by my work, took up where I left off. And nowadays, historians sometimes can't determine what was my contribution and what was his. Ptolemy's manuscript, the Almagest, was the first scientific treatise on astronomy, and his book, Geography, contains the first map of the known world. Geography and geometry both deal with the study of the Earth. Geography is concerned with making visual representations of the Earth, whilst geometry is concerned with measuring it. The shape of the Earth is roughly spherical. Let's forget for a moment that it's slightly flattened at poles and pretend that it really is a perfect sphere. You probably know, too, that all points of the sphere are at the same distance from its center. The arrow you can see now, starting at the center of the sphere and ending at a point moving on the surface, has a constant length. Let's choose an axis for our sphere, a line from the center. When we cut the sphere along a plane that contains this axis, we carve out a great circle, which divides the sphere into 2 hemispheres. If we chop the sphere up using some sort of guillotine that slices down this axis, we trace out the meridian. These are half circles going from the North Pole to the South Pole of the Earth. And now let's slice the sphere out along the plane at right angles to the axis. We get a bunch of circles called parallels. So now our sphere is covered by 2 networks of curves, the meridians and the parallels. One of these parallels should be very familiar. It's the equation, halfway between the 2 poles. For historical reasons, one of these meridians was chosen to be the principal meridian. It's the one passing through the Greenwich Observatory in England. To specify the position of a point on the Earth's surface, We can start at the point where the Greenwich Meridian meets the equator, and walk around the equator a distance measured by an angle called the longitude. Color red. Then you go up a long meridian somewhere, measured by an angle called the latitude, color green. Finally arriving at our desired destination. Any point on the Earth is precisely described by just these two numbers, its latitude and its longitude. Since we need two numbers to specify the location on the surface of the Earth, we say that the sphere is two-dimensional, and mathematicians often call it S2. Finally, if we let our little plane leave the Earth and fly off into space, then to locate it, we need to give three numbers: latitude, longitude, and the altitude above the Earth. Since we now need three numbers to say where we are in outer space, we say that space is three-dimensional. Look at the paintings on the wall. There's a portrait of Ptolemy, the father of math. How do we draw the Earth? One of them is to project it onto a plane. Let's choose a city, Dakar, for example. We draw a straight line from the North Pole through Dakar. Our line hits the table at some point. We call its projection onto the table. Any point on the Earth's surface can be projected onto the table in this way. The closer our town is to the North Pole, the farther away its projection on the table is. In fact, it can even end up off the table. For this reason, we say that the North Pole doesn't have a projection. Or, more correctly, that its projection is at infinity. The whole Earth, with the exception of the North Pole, can be represented on the plane of the table. This map of the world is called stereographic projection. Of course, our stereographic projection doesn't preserve sizes. South America appears tiny compared to North America. will roll the Earth along just like a giant ball, and will always project from the highest point. The projections of constants waltz around the planet, taking turns and becoming bigger and smaller. But if you take a closer look, you see the shapes don't change, even if lengths do. For this reason, we say that stereographic projection is conformal. What happens to the meridians and parallels under the projection? When we project from the north pole, the meridians become radii emanating the south pole. And the parallels, concentric circles. And as the Earth turns, we see that both the meridians and parallels always project to either circles or straight lines. Stereographic projection transforms circles drawn on the sphere to circles drawn on the plane. Except for those circles passing through the pole from which we project, whose projections are in fact straight lines on the plane. From this point of view, we see the meridians and parallels form two bundles of circles. All the meridians converge at 2 points, the north and the south pole. Do you recognize this one here? Yes, it's the Greenwich meridian, the end of the first stage of our journey towards the fourth dimension.
Why cannot I change? Sorry. Okay. Okay. So we just got no stereographic projection. We will meet it again the next lesson actually, but since it is important in also hyperbolic geometry, but there we will see how it relates with multidimensional geometry.
Now it's my turn to show you around the geometry garden. My name is Ashley, and I was a Dutch artist who 20th century. Geometry is a constant source of inspiration for me. I'm a past master in the art of drawing fantastic tiles. Look at this self-portrait in the spherical mirror. One of my most famous drawings shows lizards drawn on clay and manage to break out of the paper. Now, perched on high, they contemplate their previous existence as flat life. To prepare ourselves for life in 4 dimension, we are going to use the ideas behind both my engraving and a little book published at the end of the 19th century by Edwin Abbott, an English clergyman, called Flattening. Let's try to explain these flattenings, these creatures that track forever in a plane. What our everyday life in 3 dimensions is like. Let's imagine one of these lizards manages to escape its miserable existence for a moment and climbs out onto a viewpoint looking down on its world. How do we explain to his fellow reptiles the existence of objects in 3 dimensions? As a first attempt, he could try to pass some 3-dimensional objects through his flat world. Here, for example, is a tetrahedron with its 4 faces passing through the lizard's plane. The flat creatures see a green triangle appear suddenly, then gradually shrink away. This is all they see, since their senses are entirely restricted and they cannot perceive anything outside of their plane. Each time the lizards see these green polygons in the air change shape and disappear again, they might imagine the form of an object that has just crossed their plane. To see how hard to visualize the form of a geometric line from its cross-sections, try to guess what's crossing through the plane now. A tetrahedron. And now, it was a cube. Of course, you have to remember that these lizards don't have the same perspective we have. All they see is a sequence of polygons, and they'll have to develop an understanding of depth in order to fully appreciate the shape of the body. And now, an octahedron with its 8 faces. And icosahedron. It's a solid with 20 faces. And finally, the dodecahedron, 12 faces, 20 vertices, and 30 edges. Now we're going to show you some cross-sections, and only cross-sections, and you have to guess the polyhedron hiding behind them. That is a tetrahedron. That is a cube. It's getting hard, isn't it? You see now that these creatures stuck in 2 dimensions have to develop good geometric intuition if they want to understand something in the 3rd dimension that we take for granted. We don't have just the same kind of problems to get a feeling for the 4th dimension. Here's a second method to explain polyhedra to our flat friend. Start by inflating the polyhedron so that the vertices and the edges are on the surface of the sphere. Then stereographically project onto the plane of the lizards so that our 2-dimensional friends may enjoy the spectacle. Of course, we can spin the sphere around, and with it out of the keyboard, just as we did before with the Earth. Let's take a look at the cube and see how many vertices, edges, and faces it has. And now, here comes an octahedron. You see the 8 colored faces? Look how the projections of the edges are arcs of circles. Now it's an icosahedron. Its structure is more complicated, but it's not hard to understand even for the lizard. One can see 20 faces, 12 vertices, and 30 edges. Can you count them all? Finally, here's a little geometric jewel, the dodecahedron. Now, some exercises. Let's take ourselves down to 2 dimensions and try to recognize the polyhedra from their stereographic projection. It's easy, isn't it? You can see the 4 faces, 6 edges, and 4 vertices. There, it's a tetrahedron. Now, what's this one? 6 faces, each with 4 edges. That triangle is a cube. That was hard, wasn't it? The faces are triangles. 5 edges start out at each vertex. There are a lot of faces, perhaps 20. It's an icosahedron. Well done. Let's look at the dodecahedron. Each face is a pentagon. If we count them, there are 12 faces. 3 edges start at each vertex. These 5 solids are always fascinating geometry. The Greek philosophers attributed a magical importance to them by associating one of the fundamental elements from which the world is formed to each of them. We call these figures the Platonic solids. So we agree that it's not easy to get a feeling for the 3rd dimension when you are flat. There is more than one way to do this, but our stereographic projection gives a good idea of what's going on. Now, let's get ready for the 4th dimension. Prepare your imagination for a workout.
Sorry. Okay, the 3rd part. Actually, is there any questions now? Okay.
Mine is a little bit schleppy. I am a Swiss geometry. I lived during the 19th century, and I'm going to open the door to the 4th dimension. Even if I say so myself, I was not visionary. I was one of the very first to understand that spaces with many dimensions really exist, and that their geometry can be studied. If flat creatures living in the plane can understand 3-dimensional polyhedra, then why shouldn't we understand polyhedra in 4 dimension? One of my main achievements was to describe all regular polyhedra in 4 dimensions. What is the 4th dimension? A lot of been written on this subject. Science fiction writers never tire of talking about it. I wanted to explain things on the blackboard. You'll see that this blackboard is a bit of magic about it. What's important is to prepare yourself to forget about the world which is familiar to us bodies, and to imagine a new world that our eyes and our senses have no direct access to. We'll have to be smart, just like the lizard did before. I'm going to climb up to a viewpoint that, unfortunately, you cannot see. And I'll try to describe what I see from there. But before we begin, I'll draw a straight line on the board. Let me just mark the origin here. Each point on this line can be located by its distance from the origin, with a minus sign if it's on the left, or a plus sign if it's on the right. Usually, the number is denoted by X and is called the abscissa. Since the position of a point on a line can be described by a single number, we say that the line has one dimension. Now I draw a second axis perpendicular to the first one. Each point on the blackboard plane is now completely described by two numbers, usually denoted X and Y, the abscissa and the ordinate. The plane has two dimensions. If you had to explain to some being living on a line what it is to be a point in the plane that is unknown to him, you could simply say, a point in the plane is just a pair of numbers. Let's go to the third dimension. The chalk now writes in the air and draws a third axis, perpendicular to the two previous ones. A point in space is described by three numbers, X, Y, and Z. One would say to the reptiles that are curious to know about our world, a point in space is just three numbers. Let's go to the fourth dimension. One could try to draw a fourth axis perpendicular to the others, but that's impossible. So, we have to do something else instead. Of course, we might just say that a point in the fourth dimension is nothing other than four numbers. X, Y, Z, T. That doesn't help us a lot. In spite of the difficulties, we are going to try to get a feeling for this geometry. As a first attempt at understanding, we shall proceed by analogy. Here is a segment and an equilateral triangle. And finally, a regular tetrahedron. Our magical blackboard enables us to draw space. How can we keep this up in four dimensions? Observe that the segment, the triangle, and the tetrahedron have 2, 3, and 4 vertices respectively. Therefore, we can try to continue with 5 vertices. Let's go. For the segment, the triangle, the tetrahedron, an edge connects each pair of vertices. So we have to connect the 5 vertices in pair. We count. 1 edge, 2, 3, 4, 5, 6, 7, 8, 9, and 10 edges. In the tetrahedron, there is a triangular face for each triple vertice. We proceed the same way, which gives us 2, 3, 10 faces. But if we keep going by analogy, we have to add a tetrahedral face for each set of 4 vertices. There are 5 sets. That's it. We've constructed our 4-dimensional object. We'll call this the simplex. Let's spin it around in space as we did with the tetrahedron. Of course, you have to imagine a simplex spinning in a 4-dimensional space. What you see is only its projection on the blackboard. What makes things a bit complicated is that faces get tangled, and then they cross each other. Well, some experience is required to be able to see in 4 dimensions. We're going to take the simplex, which is in 4D space, and move it gradually, so that different cross-sections of it meet out of 3-dimensional space. In the same way that reptiles can see a polygon appearing and disappearing, we'll see a 3-dimensional polyhedron which appears, changes shape, and then vanishes. Here is the simplex passing through our 3-dimensional space. We're now going to meet more 4-dimensional polyhedra passing through our own 3-dimensional world. Here's the hypercube, a member of the family that starts with a segment and continues up through the square and the cube. I must confess that getting the feeling of the geometry from the slides matter like this is rather tricky. I discovered the analogs of the icosahedron and the dodecahedron. They have complicated names, but I'll just call it 120 cell and 600 cell, since the former has 120 faces and the latter has 600. Look at the 120 cell. It's just passing through our space. And now, here's the 600 cell. Of course, when I say that a 4-dimensional polyhedron has 600 faces, I mean 3-dimensional faces. Yes, these 600 faces are 600 tetrahedra. As for the 120 cell, it consists of 120 dodecahedra. In a minute, we'll see how we can get to know them better. To observe these 4-dimensional objects with our 3-dimensional eyes, we can look at their shadows. The objects are still in 4D space, but they are projected onto our 3D space, exactly like a painter might project a landscape onto his canvas. We've already done just this with the simplex. Here is the hypercube. Of course, it's spinning in space, so that we can appreciate all the details. Notice, for instance, that the hypercube has 16 vertices. Here's a newcomer. It's the most beautiful of my discoveries. An object that I call the 24 cell. It has absolutely no animal in 3 dimensions. It's a purely 4-dimensional creature. I am very proud of my discovery. Look how wonderful it is. 24 vertices, 96 edges, 96 drivers, and 24 octahedra. A real little gem. Here's the shadow of the 120 cell in all its majesty. A rather complicated majesty you have to agree. Let's get inside and have a look at the structure. 600 vertices, 1,200 edges, 4 edges start at each vertex. A completely regular structure. All vertices, all edges play the same role. It's a pity that the projection breaks the symmetry. Let's work your imagination. Imagine an object in 4D space where a huge group of rotations permutes all these vertices and edges. The champion is the 607. Like a gigantic macro molecule with its 720 edges and 120 vertices, and 12 edges starting from each vertex. Our exploration of four-dimensional polyhedra won't stop here, as their stereographic projections are bound to give us a better feeling for their geometry.
Yes, probably. Uh-huh.
The S2 sphere sits in three-dimensional space, even though it's two-dimensional. In the same way, we can study a sphere in four-dimensional space. It contains all the points that are at the same distance from a center point. But now, to determine the position of the point on this sphere, we need three numbers. This means that the sphere has three dimensions, and so our point has 3. You won't be able to see this sphere in four-dimensional space because your space has only 3 dimensions, and the screen only has 2. I can only call upon your imagination. To get a better understanding of four-dimensional polyhedra, we can do just what the lizards do with three-dimensional polyhedra. We first inflate them so that they lie on the sphere, and then project this stereographically onto the plane. This time we'll inflate the polyhedron until its faces lie on a hypersphere in 4D space and project stereographically back into our own 3D space. I'm going up to the north pole of the sphere in 4D space, and I'll project it down to you in your 3D space. You can't see where I am. Just remember how the lizards couldn't see their kinsman up on his perch-even. Now we're in exactly the same situation. Here's the simplex. You can see its 5 vertices and its 10 edges. Of course, in this view, edges are circular arcs. So now I have a situation like that of a three-dimensional polyhedra projected stereographically onto a plane. Here's the hypercube. It's easy to recognize it from its 32 edges and 16 vertices. Seeing things this way is so much easier than with the shadowing or the three-dimensional cross-sections. Here's the 24 cell with 24 vertices and 96 edges. Finally, the 120 cell. And the 600 cell. Let's add two-dimensional faces to get an even better view. The simplex with its 10 triangular faces. Of course, these two-dimensional faces are pieces of spheres, just as before when we saw that the edges were circular arcs. The simplex is spinning in 4D space before being projected stereographically. Remember when the Earth was spinning like a ball and we saw the motion of the continents? Now and again, the face passes through the projection hole, and its projection comes into it. It looks like it blows up on the screen. Let's take a quick look at the hypercube. You see the space is divided into 8 cube-shaped zones. These are the three-dimensional faces of the hypercube. As for the two-dimensional faces, they are squares, though rather than bloated and twisted. There are 24 of them. Favorite 24 cell. Look at that. The 24 cells are gorgeous. 24 vertices. 96 edges. 96 triangles. And 24 octahedron. 8 edges start at each vertex. Here's 120 cell. Let's try to understand its geometry better. Four edges start at each vertex. The two-dimensional faces are pentagons. There are 720 of them. These 720 pentagons form 120 dodecahedra. Look at all those dodecahedra fitting nicely together. Aren't they amazing?
Oh, sorry. Sorry. Actually, I wanted to say that some people are 3D printing those skeletons of four-dimensional polytopes.
Let's finish with the 600 cell with its 600 three-dimensional tetrahedral faces, its 1200 triangular faces, its 720 edges, and its 120 vertices. You can take my word for it, this object has 14,400 symmetries. Well, there you are. We're done with our first voyage into the fourth dimension. It's a dimension full of amazing things. Of course, the mathematician's imagination isn't limited to the fourth dimension. There are the fifth, the sixth, the nth dimension, and even the infinite dimension. Each dimension has its own character, but if you ask me, the fourth is the prettiest. Why? Maybe because, after all, it has a sort of physical reality. Einstein's relativity theory, dating from the early 20th century, binds space and time together into a 4D space-time. A point in space-time is an event characterized by its position in space, x, y, z, and by the time, t, when it occurs. Relativistic physics, therefore, requires an understanding of four-dimensional geometry. It's interesting to notice that the discovery of this four-dimensional geometry precedes by some 50 years the discovery of relativity. It's one of the many interactions between mathematics and physics that the history of science delights in.
Okay, questions so far? Maybe some definitions. Actually, author of this video didn't tell you how does he construct exactly those projections. No?
That's quite intuitive. You take one whole
Okay.
this year and then like that. But I have a question. Is are these regular
Yes, actually, that's the whole classification of regular polyhedras in four-dimensional space. 5, yeah. Actually, I didn't check it before the lecture. So, yeah. Symbols? What do you mean by symbols for them? Yeah. So you can find some information about them by their author, Schläfli, polyhedras. Yeah.
So, we get it right that, I mean, these specific shapes are especially convenient to imagine if we want to get some intuition about what they mean. I mean, there are a lot of objects.
Yeah, lots of objects, right. So those are probably basic and at the same time most complicated, probably, because we were working inside, not precisely inside of them, but inside their faces, inside their shadows, yeah, like this. So that's some way to start imagining these things. So actually, is there any other question? Okay, so now we have 5-minute break.
Actually, there is one more. There is hyperbolic.
Okay, yeah, I that's why I hesitated. I remembered there were 6 ones. Yeah. Yeah, 16 cells. Okay. So 5-minute break. М, Да, да, я видел такое на Ютубе. Ну, еще в книжках каких-то. Okay, dear Meatbags, let's continue. Do you want to continue the break? I don't know. Okay. You may chill for 2 minutes. I don't know. Tell me something. If you need some more rest. Today is very cold, low pressure. Okay. So I will start slowly. Oi? You can ask something if you want. Okay. So let's continue.
I'm Adrian Doherty. My entire life's work in mathematics was centered on the complex number. My contributions helped advance both algebraic geometry and the theory of dynamical systems. Complex numbers have a long history. You see here, on the left, Tartaglia and Cardano, mathematical pioneers who lived during the Renaissance. On the right, Cauchy and Gauss, who consolidated the theory in the 19th century. Complex numbers are not really as complicated as the name might lead you to believe. At first, they were called impossible numbers. Even today, they are still sometimes called imaginary. Well, it's true, it does take little imagination. Yet today, these numbers are everywhere in science and are not really mysterious anymore. In particular, one can construct beautiful fractal sets, something I worked on a lot. I even produced a film, The Dynamics of the Rabbit. It was one of the first animated films in mathematics. Let me begin by explaining the complex numbers on the blackboard. Mathematicians just love writing with chalk. You'll see in a minute that my ruler, t-square, and protractor behave rather oddly sometimes. Let's draw a graduated line on the blackboard. One of the most beautiful ideas in mathematics is to link geometry to algebra. This is the starting point of algebraic geometry. Just as we can add numbers, we can add points. Here is a red line and another blue one. Let's add these 2 points. We get a green point. 1 plus 2 equals 3. When the red and blue point move, the green point, which is their sum, must move too. More interesting still is multiplication of points. Let's look at multiplication by -2, for instance. It transforms the point 1 into the point -2, of course. And if you multiply once again by -2, you have to do the same thing. Change signs with respect to the origin, and double the distance from the origin. You get 4, of course. If we multiply twice by -2, we have multiplied by 4. Multiplying by -1 is very easy. point is sent to the symmetrical point with respect to the origin. In other words, we have a half turn, a rotation by 180 degrees, if you like. When we multiply a number by itself, the result is always positive. For instance, if we multiply by -1, we make half a turn, so that if we do it one more time, well, we come back to the initial point. This is why -1 times -1 equals +1, simple enough. You see, for instance, that multiplication by -1 sends 2 to -2, and then if you multiply one more time by -1, you come back to 2. Obvious, isn't it? Therefore, there is no number which, multiplied by itself, yields -1. Another way of saying this is that -1 has no square root. But of course, we are underestimating the inventiveness of mathematicians. At the beginning of the 19th century, Robert Argand had a really great idea. He said to himself, since multiplying by -1 is a 180-degree rotation, its square root is a rotation by 1/2 of 180 degrees, 90 degrees. If I do 2 quarter turns, one after another, I end up doing a half turn. The square of a quarter turn is a half turn, hence -1. It's easy when you know how. Argand decided, therefore, that the square root of -1 is the point where 1 ends up after a 90-degree rotation. But of course, this forces us to leave our horizontal straight line, since we just agreed to assign a number to a point that's not on a line. Because this construction is a bit strange, we call this point the square root of -1, an imaginary number, and label it I. But once we have the courage to leave the line, everything else is easy. We can represent 2i, 3i, and so on. Each point in the plane represents a complex number, and conversely, each complex number defines a point in the plane. Points in the plane become numbers in their own right. These numbers can be added just like usual numbers. Look at the red point, which is the point 1 plus 2i. Let's add 3 plus I, which is the blue root. Well, we add them just as school children do, giving 4 plus 3i. Geometrically, this is just addition of vectors. You see that it's no problem to add complex numbers. Much more interestingly, these complex numbers can also be multiplied, just like real numbers. Let's see. We know how to multiply a complex number by 2, for instance. 2 times 1 plus I gives 2 plus 2i. Geometrically, multiplying by 2 is easy. It's just scaling up by a factor. If we double the red point, we get the green point. Multiplying by I is not difficult either, since we know that I corresponds to a quarter turn. In order to multiply 3 plus I by I, we just have to rotate by a quarter turn. We get -1 plus 3i. Not so complicated, these complex numbers. And finally, we can multiply any 2 complex numbers with no problem whatsoever. Let's try, for instance, to multiply 2 plus 1.5i and -1 plus 2.4i. We proceed as usual. We first multiply by 2, 1.5i. Then we have the results. Therefore, we get negative 2 plus 4.8i minus 1.5i plus 3.6i times I. But recall that I squared is negative 1, since we invented I for this purpose. This gives us negative 2 minus 3.6, etc. Let's clean up a bit. We find negative 2 minus 3.6 plus 4.8i minus 1.5i. That's negative 5.6 plus 3.3i. There you are. We know how to multiply complex numbers. In other words, we can multiply points in a plane. Amazing. We thought the plane was two-dimensional, since two numbers are necessary to locate the point. And now, I'm telling you that one number is enough. Of course, we changed our numbers, and are now dealing with complex numbers. Now's a good time to define two notions, the modulus and the argument of a complex number. The modulus of a complex number z is just the distance from the origin to the point that represents the plane. Let's use the ruler to determine the modulus of the red point, which is 2 plus 1.5i. Let's see, it measures 2.5. The modulus of 2 plus 1.5i is therefore 2.5. For the blue point, I get 2.6. And for the green point, which is the product of 2 points, I get 6.5. What's the rule? The modulus of a product of two complex numbers is just the product of the moduli of the two numbers. The argument of a complex number is measured by the angle between the abscissa axis and the straight line joining the origin to the point. Here, for instance, the argument of the red complex number is 36.8 degrees. The argument of the blue point is 112.
Actually, we can speed up if this is something known. He will define a complex number for the next 2 minutes straight. Okay. I take this as so. Okay, if no one disagrees, I will skip this video. Yeah.
I'm going to show you some transformations. Transforming what? Well, if you don't mind, we'll transform my portrait. Let's go things simple. The transformation z goes to z over 2. Each point on the photo corresponds to a complex number z that's divided by 2. We get another point. It's imaged by the transformation. Hence, a new picture. You see, no surprise. I just shrank half my size, since each z has been divided by 2. This transformation is called a dilation. How about the multiplication by I? Easy. We know that multiplying by I is just a quarter term. Note that the modulus doesn't change, but the argument increases by 90 degrees. Indeed, this is quite a sophisticated way of saying just rotating the picture. Well, a bit more complicated. Multiplication by 1 plus I. Look at the complex number 1 plus I, corresponding to the point we have CISO 1 and ordinate 1. Its argument is 45 degrees, and its modulus is the square root of 2, using the Pythagorean theorem. Hence, multiplication by 1 on the side amounts to first multiplying its modulus by the square root of 2, and then adding 45 degrees to the argument. In simple words, you have to combine a dilation and a rotation. This is called a similarity. More interesting, we are going to transform the points z into their squares, z times z. Let's begin by placing the photo in a suitable place, flush against the coordinate axiom. Then I zoom a little bit, since the squaring process will change the size of things, and I need enough space to show you this. Okay, now we can transform the photo progressively. Notice that the argument of z squared is twice the argument of z, so that the right angle on the lower left of the photo is doubled under the transformation. It's turned into a 180-degree angle. Let me place this photo somewhere else, and let's look again at the same transformation, z squared. You'll notice again the same argument double. Look, for instance, at my index finger transformation. Its argument is about 45 degrees. And after the transformation, it points upward at 90 degrees. But you can also observe that moduli are squared. Now let's go to a new transformation, setting the point z to negative 1 over z. Don't forget, with complex numbers one can add, multiply, but also divide. Not zero, of course. Doesn't this image remind you of the Sistine Chapel? Large complex numbers with large modulus become small when one takes their inverses. And conversely. Here is a similar transformation. Look at the formula. The value of k changes slowly. Some parts will expand, others will contract. But if one looks closely, the shape is preserved, even though lengths are not. A circle remains circular, even though it might grow. My hand grew. My face became smaller, but you can still recognize them.
So these are phenomena that we will see in hyperbolic geometry, actually.
One more transformation. Well, this was not really a weight loss program for me. But note once more that even though I got bigger, the shape of small parts did not change. If you look, for instance, at a button on a shirt, it keeps a circular shape. We say that these transformations are conformal or holoformal. Right, the complicated Latin and Greek words for saying that they preserve shapes. Indeed, with complex numbers, you can do quite a lot. You can even take the exponential, if you know what this means. But even if you don't, look at the treatment I have to suffer from the exponential. Has my head disappeared? No. If you look through a microscope near the origin, you could see my beard. Now that you know about complex numbers and have seen some transformations, I'll explain some of the objects I've been studying. Here you see a number of points. Some are blue inside the disk, and some are yellow outside. Let's perform the transformation z squared several times and look at the result. You can see that the blue points stay inside the disk, while the yellow points escape from the disk, and even escape from the screen. We say that the blue disk is the filled-in Julia set of the transformation z squared. Points outside the Julia set escape to infinity when one repeats the transformation indefinitely. But we can play the same game with other transformations, like, for instance, those of the form z squared plus c, where c is a complex number that we will choose at will. For each complex number c, we get a Julia set whose shape changes when c changes. You can see a few examples here. Here's the one I call the rabbit. In order to understand how these shapes change, I'll show you several things in parallel. On the left side, the red side, you get a point that starts to move. This is the point C. On the right side, you see the corresponding Julia set. It's deformed as C slowly changes. But sometimes, for some values of C, the Julia set seems to disappear, and we can't see anything on the screen anymore. Like now, for instance. The truth is that the Julia set blew up into an infinite number of pieces so small that you don't see anything on the screen. Benoit Mandelbrot, who popularized fractal sets, suggested the study of this set drawn in red that describes the values of C, for which one can see the Julia set clearly on the screen. In other words, those for which the Julia set does not blow up into multiple pieces. Of course, this red set is called the Mandelbrot set, and I spent my time studying. To finish, let's look closely, very closely, at this Mandelbrot set and zoom inside so you can appreciate how beautiful it is. Let's go. Here it is. Admire. For once, I won't explain everything. Imagine the Mandelbrot set as a black island surrounded by a tropical sea, and then you can see the bottom of it. Really looking at truly microscopic details. If the Mandelbrot set were the size of a soccer field, we'd be looking at details the size of a single atom, on the order of a millimeter. Maybe you're wondering why I got interested in this. First of all, because it's beautiful, and because understanding these objects gave me much pleasure. For me, this is reason enough to spend time on these questions. But also, because in these transformations that look so simple, we can find the essence of chaos, such a fundamental concept in modern science. Simple things generate rich structures. To study complicated phenomena through their simplest incarnation, this is often the role of the mathematician.
Where? Where? On the what? Ah, yeah, actually, I don't know what this you mean. Probably, I don't know actually. Probably there are several, I don't know. Sorry.
Circles in space, arranged to create beautiful ornaments. In order to better understand the three-dimensional sphere in four-dimensional space, I'm going to show you how to fill space with circles, and thus create what mathematicians call a fibration. By the way, my name is Heinz Hoff, and I'm one of the main contributors to the development of topology during the first half of the 20th century. Look at this torus filled with circles that appear to be linked. Let me explain this to you. Circles, spheres, and tori are among the simplest objects studied by topologists. A topologist tries to understand the connections between these objects. I worked in Berlin, Princeton, and Zurich, and one still comes across my name often in contemporary mathematics. Quantum Hopf theorem, Hopf invariant, Hopf algebra, Hopf vibration. Let me paint my portrait for you. I published the discovery of my vibration in 1931. But, as always, I have to say that I rely on many predecessors, like Clifford, for instance, whom you see here, and who worked in England during the 19th century. Let's begin with some explanation of a black hole. Well, a white hole this time. What do you see? A two-dimensional plane? Well, yes and no. This is indeed a two-dimensional plane, but it's a plane with two complex dimensions, or in other words, a space with four real dimensions. Give it a try. Each point in this plane is determined by two coordinates. But each of these two coordinates is a complex number, which, remember, is itself defined by two real numbers. Each of the axes is a complex line, so each point on a given axis has one coordinate, which is a complex number. For instance, here you see the point 2 minus I on the first axis. The same is true for the other axis, the y-axis. Here we can see the point 1 minus 2i on this axis. Now, our whiteboard is magical, but not enough to be able to show us the two planes simultaneously. If we try to depict them in three-dimensional space, they will intersect along a line. In four-dimensional space, they intersect only at the origin. After all, they are axes. Now what do you see? A circle? Yes and no. What you see, or rather, what you should imagine, is the set of points in four-dimensional space that are a distance 1 from the origin. In other words, this is nothing other than the three-sphere, S3. Well, of course, you need to have a little imagination. Let's try to see at least how this sphere intersects the first axis. The 3 intersects the first axis in the set of points on this axis, which are at a distance 1 from the origin. You see, the 3-sphere intersects the first axis in a circle. The same is true for the second axis, which intersects the 3-sphere in a circle as well, the blue circle. Now, what is true for the horizontal line and the vertical line is equally true for all lines going through the origin. Here you can see the line of Z2 equals negative 2 times Z1. But we could do the same with any line. Z2 equals A times Z1 for any complex number A. In this manner, the 3-sphere in four-dimensional space is filled with circles. One for each complex line through the origin in our plane of 2 complex dimensions. Careful though, in the picture you get the impression that the red circles intersect each other. But this is not the case in four-dimensional reality. Lines are only at the origin, so their intersections with the unit sphere don't intersect at all, in fact. I discovered some very interesting things about this decomposition of the sphere into circles, and ever since it is known as the Hopf vibration. Why vibration? Well, you could think of the fibers of fabric. We're going to look at all that using stereographic projection. Imagine we project the 3-sphere from the North Pole onto the tangent space at the South Pole, which is out of 3-dimensional space. Here is the projection of one of the circles, which, as we have seen, is the intersection of one complex line and the 3-sphere. But there are many such circles, one for each complex line going through the origin. For each complex number A, we can consider the line Z2 equals A times Z1 and its associated circle. Let's vary this number A, or what will amount to the same thing. Let's rotate this line in order to see how the circle changes. Notice that sometimes the circle appears to be a straight line. This is simply because it passes through the North Pole of our 3-sphere. Let's look at 2 of these circles simultaneously. In the lower left-hand corner, you see 2 moving complex points, one red, the other green. You can see the circles associated with the red and green points. Note that these 2 circles are linked together by 2 links of the chain. It is impossible to separate them without breaking them. Just for the fun, let's consider 3 circles. See how the 3 linked circles dance together? see many more complex lines chosen randomly, and let's look at them all at once. The circles fill space, and no two of them intersect. This is an example of a fibration. Let's try to understand this better by returning to the board. Look, we have a hot circle for each line. Each one of these lines has an equation of the form z2 equals a times z1, where a is a complex number, the slope of the line, and is indicated by the red point moving on the green line. Actually, the vertical axis does not have such an equation. But in this case, we may say that a is infinite. Don't forget, a is a complex number. The green line is also a complex line, so it's a real plane, of course. Summing up, the complex lines that we are interested in are completely determined by a point on the green line and an additional point at infinity. But we already saw that if we add a point at infinity to the complex line, we get the usual two-sphere. Once more, this is stereographic projection. So, the complex lines that interest us are parameterized by points on the yellow sphere, the two-dimensional sphere S2. So we have a circle for each point on the two-sphere. But a circle is a one-dimensional sphere, isn't it? All these circles fill up the three-sphere. Each point on the three-sphere belongs to a single circle and therefore defines a point on the two-sphere. In this way, we get a projection from the three-sphere to the two-sphere. Complicated, isn't it? Mathematicians say that above any point of the base, S2, there is a fiber, which is a circle, S1, and that the total space of this vibration is here, S3. I am very proud of my vibration, all the more so because it has become a fundamental object in topology.
Okay. Any questions so far? No? Vibration in general, what does it mean? Yeah, actually, it is when you when you have some mapping, mathematically speaking, or for example, projection on some subspace, and pre-image of each point is for each point is looking alike for each point. I mean, yeah. So it's somewhat like the same. Usually, so if they are more or less equivalent, like equal, like for example, they can be moved to each other, or equal by some other means, then this is called hyperbation in general.
Let's come back to the two-dimensional sphere and its parallels. Above each point of the two-dimensional sphere, we should imagine a half circle. Look at what's above the parallels S2, the equator, for instance. Here's what's above another parallel, which is moving southwards. Why is the torus thinner? Because above the south pole, there's, of course, only one circle. And above the north pole, you see a straight line. Actually, a circle going to infinity. This is the red. Well, let's spin all this around. Rotations, yes, but rotations in four-dimensional space, of course. To be honest, I must admit, some of these pictures were already known long before me. The existence of four families of circles on the torus is usually attributed to the Marquis de Larsen. But one finds earlier clues in the sculpture in the Strasbourg Cathedral, for instance. Take a torus of revolution. This is the surface described by a circle rotating around an axis in its plane. Slice the torus with a plane. Notice how I chose the plane. One says that it is bi simply because it is tangent at 2 points. Now, look carefully. Plane cuts the torus along 2 perfect circles. This is the large sphere. The plane, which is bitangent to the torus, cuts it along 2 circles. Of course, there's not just one bitangent plane. Here's another one, cutting the torus along 2 other Larsen circles. And we can do the same for all other bitangent planes. We just need to rotate around the axis of symmetry. You see, another is a meridian. Then a first Larsen circle, and a second one. And since one can do this at any point of the torus, we see that the torus is covered by 4 families of circles. 2 circles of the same family do not intersect. A blue circle intersects a red circle at a single point. A yellow circle and a white circle intersect in 2 points. These are the Larsen circles. Take a good look at the yellow circles. These are hot circles. Remember when we looked at what is above a parallel in the vibration? We saw a torus covered with linked circles, just like this torus covered with the yellow circle. And what about the white circle? Well, there the fibers of another off vibration. The mirror image of the first one. To finish our stroll, we'll take a tourist revolution with its 4 families of circles. Imagine it as a 3-dimensional sphere. Rotate the torus inside the 3-dimensional sphere, and finally, project it stereographically onto 3-dimensional space. In this way, we obtain surfaces that are also covered by 4 families of circles, the so-called Dupin cyclones. Sometimes when the torus passes through the projection pole, the surface becomes infinite. In this movement, the 2 faces need to be switched. The inner face of the torus is pink, and the outer one is green. A simple rotation in the 4th dimension, and bingo, green turns into pink, and pink into green. Isn't that magnificent?
Okay, any questions so far? No? Okay, so actually we will see also some other things today, but this will happen before, after 5-minute break. Yeah, so let's have a break. So how should I sign Birner Schickel-Gruber in the chat?
Это Петр Кушнир.
Huh? Didn't hear you.
Петр Кушнир.
Still don't hear you. Okay. Okay. Now let's continue. So the final part of Dimensions movie. Then we will move to something other than this. So this will be some technical notion important for later lessons.
Doing mathematics means above proving what one claims. We've seen that stereographic projections and circles on the sphere not going to pull to circles. And now we're going to prove it. Even though this has been known for many centuries, it is I, Bernhard Riemann, who will present this proof to you. And frequently I, as one speaks today of the Riemann sphere. Proving is much more than showing. It's not enough to see in a movie that some curve looks like a circle to be sure that it is indeed a circle. A mathematical proof must use reasoning to be convincing and must explain why it is indeed a circle. The great Euclid, during the 3rd century before Christ, formulated the rules of the mathematical game in his book, The Elements. To rely on facts that themselves have to be proved. But one has to start with something, so that some statements have to be accepted without proof. These are the axioms. Therefore, mathematics appears as a gigantic construction whose foundation consists of the axioms, and such that each brick rests on the previous ones. In order to prove the theorem about the stereographic projection of circles, we should in principle start with the axioms. Of course, we have no time for that now. We'll assume we already know the theorems of geometry that are often studied in high school, and we'll prove this theorem. Start with something simple. The intersection of a sphere and a plane. We see that if a plane cuts a sphere, and if it is not tangent to the sphere, then the intersection is a circle. We can see it, but why is it true? How do we prove it?
Okay, let's skip this part.
In priori, no, we still have to prove it as A. Well, because they are both right-angled triangles having a common hypotenuse, and the sides CA and CD have the same length. Why? Well, because these are two radii, of course. You see, if we had to go to the end of all the arguments, this one would be the longest in movie history. Look, we proved that any circle drawn on a sphere can always be thought of as the contact locus between a cone of revolution and a tangent sphere. If you like, a sphere is like ice cream in a cone. Well, we shouldn't forget that our aim is to show that stereographic projection carries circles onto circles. Let's first prove what mathematicians call a lemma. Here is the tangent plane to the sphere at some point A, seen from the side. Now, here's the tangent plane at some other point B, and also seen from the side. These two planes intersect along the line D, but presently we see only one point, since this line is perpendicular to the screen. The figure that you're looking at is symmetric with respect to the bisecting line of the two lines on the scene. This three-dimensional picture is symmetric with respect to the bisecting plane of the two tangent planes. Choose some plane containing the segment AB. It intersects the line D at a point M, unless it's parallel to D, of course. The figure's symmetry with respect to the bisecting plane shows that AM and BM have the same length. The triangle ABM is isosceles. Voila! That was our lemma. Now we can prove our theorem using what we just learned. Consider a circle of the sphere which does not go through the North Pole. We want to show that its projection is a circle. Look, if instead of projecting onto the tangent plane to the South Pole, we projected onto some other parallel plane, the famous theorem of Thales would imply that all projections are similar. Hence, in order to prove our theorem, we may choose the projection plane as we wish, as long as it is parallel to the tangent plane to the South Pole, of course. So let's place our yellow circle in a cone. Remember, the ball of ice cream in a cone with vertex S. Well, we are going to project onto the horizontal plane through S. The point B projects onto a point D. But look at the figure. The triangles A and B and DSB are similar. Why? Well, again, Thales' theorem. Do you agree? Now, remember our dilemma. The triangle ABM is isosceles. Hence, the same is true for the triangle BDS, so that BS has the same length as DS. When B moves along the yellow circle, the segment BS stays tangent to the sphere. Its length, therefore, remains constant. Since BS and DS have the same length, the moving segment DS also maintains a constant length. Let's see, saying that DS is a constant length means precisely that D describes a circle with center S, so that the projection of our yellow circle on the horizontal plane through S is contained in the circle. We have seen that by Thales' theorem, this implies that the projection on the tangent plane to the South Pole is also contained in a circle. And this is what we want to prove.
Okay, actually this theorem is much more comfortable to prove in coordinates.
Yeah, because I remember it from my international analysis course. It was
Okay. So at least, okay, so at least we proved something in this course. Finally, okay. Well, we didn't prove quite formally about the triangle area formula. Okay. Sorry. Yeah. Okay. So this is how. So this is game footage. Actually, it is still in development. I'm waiting it for 10 years already. The name is Miega Kuria. I don't know how to pronounce it. Okay, you can find some information about it in the web. Okay, some puzzle game.
You get pretty free, a game where there's a fourth dimension space. So I thought I would show you what it would actually look like if you could walk through walls using fourth dimension. And in the process, explain what the fourth dimension is. So say you need to get to the outside of that wall, but you can't jump over it and you can't walk around it. But what if there was more to this one? What if you could just walk around the wall in the fourth dimension? So you turn to visit on the fourth dimension, walk around the fourth dimension, and turn back. You discover that the walls disappeared, and it's been replaced by a bottom level that you replace with. So say you have this free character and you need to get to the other side of that wall. You can't jump over it, and well, that's fine. But what if there was more to this world? What if the world was actually 3D and you were just a 2D flat character that could only move inside a 2D plane? You could go past that wall by just sidestepping it, but how do you do that since you're stuck on the plane? So you press the button to turn sideways, and now when you're moving left and right, it doesn't mean the same thing. It actually means moving along the third dimension. So you take a few steps, and you press the button again to the direction away, but now you're in the world that is further along the third dimension. So the wall is not in front of you anymore, it's up to the side, and you can walk right past it. You notice that some rubble is falling off the wall in the third dimension also. You turn sideways and take a few steps to get out to where you came from and turn. Okay, this little tree character is only two, I guess he can't see the third dimension. So what does he see when he turns sideways? He might think the world is deforming, but it's just what it would look like if you took 2D steps to go to 3D objects, like images produced by an environment change, for example. The world isn't changing, it's just being seen from different directions. So when he's struggling on the third dimension, down in the desert world, he can't see the wall, but he can see the road. And from the sideways perspective, he can move across worlds back into the past. But back to figure problems. What if the world actually had 4 dimensions, but we could only see 3? In other words, what if you were living on a 3D plane inside a 4D world? So you press a button to turn sideways. And now, when you're moving this way, it doesn't mean the same thing it used to. It actually means moving along the fourth dimension. So you take a few steps, and you press the button again to visit a different way. But now you're now a fourth dimension. So the wall is not in front of you anymore, but off to the side, and you can walk right past it. And you can notice that some rubble is falling off the wall in the fourth dimension. You turn sideways and take a few steps to get back to where you came from, and turn back. And this is how you walk through walls using a fourth dimension.
Okay. So now we will see how to slide in dimension, how to slide across some axes. It's the same game.
The world we're building in Meatbags is a world in which there are 4 spatial dimensions instead of 3. In this game, the 4th dimension is not time, but the 4th dimension is space that works just like the first 3 dimensions you're familiar with. If you count time, this game is 5D. In this video, we'll talk a little bit about the unique technology developed for the game. So, at first, games were only 2D and only took place along 2 directions. Then computers became powerful enough to run 3D graphics, and this allowed for full 3D movement. Of course, the graphics we see while they're computed in 3D are actually displayed on a 2D screen. They are projected down from 3D to 2D in a way that makes our eyes perceive the third dimension. But it doesn't stop there. If in a 2D game, every object's position is represented in the computer using 2 numbers, and if in a 3D game, every object's position is represented using 3 numbers, what if its position was represented using 4 numbers? In other words, what if long in addition to the first 3? Trying to answer this question is what led us to develop this game. However, as far as we know, one universe has exactly 3 spatial dimensions, so it's difficult for us to picture what a 4-dimensional world. But a computer, on the other hand, does not care. It's just working with numbers as usual. So we had to come up with a way to display this calculated 4D world so that our 3-dimensional brains could comprehend it. The way we chose is a method that has been popularized in the novella file. This novella talks about a 2D square that can only see a 2D cross-section of the 3D world. For the square, the third dimension is invisible and mysterious. The square has no concept of it because it is stuck seeing a 2D world. If a 3D object visits the 2D plane, it appears to be deformed. In Hyperbolic, a similar process happens but in one higher dimension. Instead of taking a 2D slice of 3D objects, we are taking a 3D slice of 4D objects. It's hard to imagine, but luckily we don't have to. The computer could just display it for us. But how to build a 4D world when the objects are populated, especially without being able to fully see them? In a 3D game, objects the surface of the 3D object is 2D, and triangles have a surface 2D shape. To generalize this concept, we add a dimension. The surface of a 4D object is 3D. So what is the simplest 3D shape? It's a pyramid-like shape called the tetrahedron. So to build the surface of any 4D object we want, we can use the tetrahedron as a building block, and that's what this game does. What happens is that instead of projecting the tetrahedron on the screen like we're doing now, we slice them using the 3D plane that represents what the player can see. That gives us a bunch of triangles, which we then draw the same way when we draw them for a regular 3D game. What you see is a 2D projection of a 3D slice of a 4D object. But how do we even create 4D objects? We can't easily visually manipulate them using a 4D equivalent of Maya, but what we can do is generate them procedurally. So let's take a simple example. To build 4D crystals, we use a method similar to how we would build a 3D crystal procedurally, but instead of starting with a 2D hexagon and extruding it up, we start with a 3D dodecahedron and extrude it into the 4th dimension. I picked the dodecahedron because it often gives hexagons when you slice it. Every crystal is the exact same shape, only facing different directions and slightly longer or shorter. And yet they all look so different because you only see a slice of each other. This is particularly interesting because of the known connections between high-dimensional space and certain crystal structures. I can move a little bit in the 4th dimension and the scene will look slightly different, and again, slightly different. There are technically an infinite number of unique slices we could take. Here's another more complex example. The surface of this 4D shape, called the 120 cell, is made out of 120 dodecahedra. In this case, I cut a hole inside each dodecahedron to make them hollow. While you could ignore all this when playing a game, to me it feels even more beautiful when you know about what's happening. I wanted to share some of the things you may not realize when you finally get to play Meatbags.
Okay, so actually this game is still in development, as I said. Developer is posting something like he's developing some puzzles for it. Actually, he already published some game like 4D toys. I'm not sure we will watch this video since we don't have enough time. You can watch it by yourself on YouTube. Okay. So about it. So I found some quite nice explanation of multidimensional geometry, how can you imagine it? Yeah. So this is some esoterical website. Since they are kind of interested. Okay, so first dimension, second dimension, third dimension, trivial, fourth dimension time, already heard about it. Okay. Fifth dimension. So we can think about all possible worlds, like all possible things happening. Actually, we will later. So this might set one parameter for what is happening. Okay, this was 5 dimensions. So sixth dimension is when you start. So is the timeline with the same start conditions. Yeah. Seventh is when you set different start conditions. So if you are branching each situation infinitely for one parameter, like, yeah. Ninth dimension. Okay, so varying laws of physics, like varying physical constants or something like this, like gravitational constant, speed of light. It might be some absurdist worlds, yeah. So possibility. So this was some short and sometimes silly explanations. Let me go away from it. So there are several others actually. Okay, so this was what I saw through and some examples that I found on the internet. So let us imagine the so-called advanced twin paradox. Advanced twin paradox, yeah. The original twin paradox is when Alex and Borex are twins, and one is traveling faster across the timeline than the other. This was an imaginary experience from relativistic theory from physics. And advanced situation is when they are born with identical genetic diseases. So Alex, who is Borex, and Borex is young, is older for now. He tells Alex what will happen later with Alex, yeah? So Alex lives with knowledge of what will happen with him next. So this is some imaginary experiment, yeah? Okay, so that's what I said earlier. We can vary physical constants. In such universes, there might be maybe no life, no planets, and you can try to vary them. And how do we experience many dimensions in life? For example, we are developing, and we have parameters like idea to invest, invested capital, maybe some other parameters. So each parameter adds another dimension, and we prognose for each setting of parameters what will be the outcome. So this might be this might take some long time to do, but yes, this is the way. So when you plan the day with different possibilities, so memory is another dimension of our living, just backward time, yeah. So some physical dimensions. Actually, at Moscow State University, at mathematical department, we were studying physics in a way of phase space. This is when you add to standard three coordinates, three other coordinates of your velocity. Yeah. So this will form a six-dimensional space. So here is a diff on the right side of the screen. And for real space and phase space. So when you are studying n objects physics, you just form many dimensions, 6 plus 6 plus 6 plus 6, yeah. And actually, when you are controlling like another mechanism, you are already experiencing 6 dimensions, since you are in 3 dimensions, moving your body in 3 dimensions, and moving drone in 3 dimensions. And also maybe some complex motions of your body form 2n-dimensional space for n is a number of your joints. And actually there is some complications with this, because, for example, fingers are not so free to bend. There is some, I know some beautiful notions that if you are trying to bend your finger, right, this will, these 4 points on joints, yeah, they will form a circle for most of the people. Actually, I once saw a counterexample. One schoolgirl showed me how she can bend her finger, and this law somewhat broke. But yeah, for most people, this will form a circle. You can check it by yourself. Okay. So some restrictions. Okay. So some other ways to experience many dimensions. So we have like 6 senses, and actually, actually is you may consider is 3-dimensional perception, because there are 3 dimensions of colors. There is a red, green, blue model, which is about how the light, how the color is decomposed inside our eyes. So there are dimensions of sound. There are dimensions of smell, since we have like several parameters for smell. So several parameters for taste, many dimensions for tactile sensations, since this is formed. And yeah, so maybe 6th sense. I already talked about probabilities, so we can imagine something while we are moving. So this add another 3 dimensions to us. Some maybe emotions, like I found 5 parameters in the internet. Maybe there is more. I don't know. Okay, so actually, just to sum up what we have studied today. So there is an algebra. So how to reason in many dimensions. Before we were discussing what is about imagination of multidimensional geometry. So how to reason? There is an algebraic way in coordinates. We have seen this in Mega Curie game. So there is a geometric way in relation between objects, processes, interactions, places, main success in 4D toys game. So you can rotate your 4-dimensional objects. Actually, this game is already out, so you can play it. So there is a frontal way in relation with outer objects, like we see in Dimensions movie. And there is a combinatorial way, like we may organize the space in different ways. So we will see this in the next slide. Okay, there is some, this is what I found on the internet. Actually, this is some visual sum of cubes. You may consider, why did I choose sum of cubes? Actually, for example, if you have sum of squares, then how do you organize sum of squares? In which sum of squares? So here is 1 cube plus 2 cube plus 3 cube plus 4 cube, yeah, and so on, plus n cube. And there will be a formula for summing this up. Short formula, actually, without any dots in it. Yeah, you can complete it shortly. And for example, if you are trying to sum up squares for first n natural numbers, like 1 square plus 2 square plus 3 square plus 4 square plus etc. plus n square, you just form a pyramid. So you may consider 1 square as the top layer of pyramid, yeah, 2 square as the second layer, 3 square as the third layer from the top, n square is lowest layer for the pyramid. So for coordinate way of thinking in 4 dimensions, and when you sum up cubes of first n natural numbers, then you are just forming a 4-dimensional pyramid with 1 cube at the top layer, 8 cubes at the second from the top layer, and so on. Yeah, and we will see how to reorganize pyramid in a different way. So actually, this is just another way of thinking about this. Yeah. Okay. Okay, so maybe, I don't know, does anyone need to explain? No? Okay. So, this was some ways to live and think in many dimensions. Yeah. So, questions so far? Any questions so far? Okay. So, everything was clear, right? Okay. Yeah? Okay, so now let's finish our lesson. We will see you in Thursday. Okay.